Okay, so question 1. Determine whether the following reaction is a possible decay for the neutral pion, pion 0 there, so the 0 showing you it's neutral. Okay, so if you ever get a question like this, you need to think about obviously your conserved quantities, right? So strangeness, charge, baryon number, lepton number. Okay, so charge you can normally see quite easily, it's a neutral. So this one's going to have 0, right? And then we're going to say, well, the electron is going to have -1, okay, positive muon, and 0 for our neutrinos. Okay, so charge is conserved. We can see that. So if we're then going to talk about, well, any of the others, baryon, okay, you do need to remember that hadrons are quarks, okay, particles containing quarks, and therefore you're going to need to remember the different particles in terms of mesons and baryons. Okay, baryons being 3 quarks and mesons being 2 quarks, right? So baryons here, there aren't any. Okay, so pions you can recognize as just having 2 quarks and being a meson, and then everything else here is a lepton. And that's our next one, right? So lepton number is going to be tested by 0 to start with. Like we say, that's a baryon, so that's not got any. So we need this to balance with 0. Okay, now an electron is a standard particle that is a lepton, so you'll have a +1. If you ever get confused about whether or not you have a lepton, okay, don't forget to use your data sheet. Okay, so we're going to be using this area here obviously for the properties of quarks, and we're going to be using this area here for the properties of leptons. Okay, so you can see here it lists your leptons. So we've got +1 for our electron, we've got -1 for our positive muon, okay, because obviously that's an antiparticle, and then we've got the neutrinos as well, right? And we use the neutrinos to balance the lepton numbers in these decays. So here we've got an anti-electron neutrino and an anti-muon neutrino. Those are going to be -1 on the lepton number. So if we go back to the question, you are going to get -1 and -1. Okay, so you're going to be able to say that the lepton number is not conserved, therefore this decay is not possible. Okay, when you do that, you need to do this as well. Okay, you need to show that, preferably if you are doing questions like what we're going to do in a second, you're going to show it by quarks, by the sort of properties of quarks, but you're going to at least want to show that you understand the properties by doing this kind of demonstration. Okay, so I'll show you the mark scheme for that. So you're going to show the lepton number is not conserved, therefore this isn't possible. Lepton, and then you get the second mark for the lepton numbers for the particles being correct. So you should have 0, +1, -1, -1, so therefore giving you a total of -1. Okay, and you've also got the muon lepton number isn't right, because obviously you should have conservation for muon and electron lepton numbers individually, and you've got -1 and 0s for everything else. Okay, so either of those would have got the second mark, but you need to do a demonstration like this, and then you need to state clearly that the lepton number is not conserved, therefore this is not possible. Okay, stating 2 possible quark configurations of a pion 0. Okay, so again, you remembered it's a meson. Okay, so you're going to look at your quarks and say, well, here, that's a reminder that baryons are obviously 3 quarks, but you are going to need to remember what particles are baryons, which are mesons. Okay, so you can say here, well, in that case, what's going to need to be the case here is that the baryon number is going to be +1/3 and then -1/3. So it's going to be one of these particles and then an antiparticle of something else to accommodate for that, right? So if we're only doing 2 quarks, okay, obviously if we have, let's say, an up and then an anti-down, the charge doesn't match, right? We also need the charge to be neutral. So +2/3 charge and +1/3 baryon with a strangeness of 0, we would be able to make that into an antiparticle, and we would be able to go, obviously the anti-up would give us -2/3, -1/3, the strangeness doesn't change. Remember, you're not going to be dealing with many strange particles, mainly the kaon. Okay, so we'll be able to say up and anti-up, and down and anti-down are the two possibilities, because that's the only way that charge comes out of neutral, and our baryon number remains 0, and everything else is conserved. So a student suggests that the kaon and the anti-kaon are the same particle. Discuss whether this suggestion is correct. So to talk about that, you need to again talk about the quarks, and here you're going to need to try and remember that a kaon has a strangeness of +1. It is a meson. Okay, so the first mark is for identifying the quarks, okay, or basically proving this by identifying the quarks. So against meson, it's going to have 2. So it's going to need to balance otherwise, okay? We can't just have random +3rds baryon number left over. So if we do a +1, okay, we're going to have an anti-strange with +1, -1/3, and +1/3 charge. So then we're going to need to balance that out, okay, with down quarks, okay? So if that becomes +1/3 for an anti-strange, we would then have to say, well, that means a standard down would bring that back down, a standard down would bring the 1/3 baryon number back up, and it wouldn't affect the strangeness, leaving us with a +1 strangeness, okay? So you'd be able to say that a standard kaon, because we do need that strangeness to be +1, you would have down and an anti-strange, and then the anti-kaon would be the other way around, right? Anti-down and a strange. So therefore you can say that whilst they share a lot of the same properties, you're going to get the marks for saying that, I'll show you again here, you're going to get the marks for saying, identifying the quarks, and then stating that the strangeness is not the same. So therefore they are not the same, and the statement is not correct. Okay, so identification of quarks with the kaon correct. Okay, so that's an important one there. That's a bit of recall for that. And then with statement that they are not the same particle, and therefore the student is not correct. Okay, don't forget, when you have these lines, a lot of you be doing some great sort of maths to show what you were thinking, but if you have these points about discussing things, okay, or clearly stating things, you need to add in the statement as well. Have a look at how many marks you have for what you need to do, and think about what these marks are going to be marked for. Okay, and that brings me on to the last one, which is a 4-mark question, right? And the nucleus is held together by a force. It was predicted that a particle exists that is responsible for this force. The particle itself must experience this force, right? So we've got some factors starting to come in that we need to make sure we tick off. The particle would have a rest energy between that of an electron and a half of a nucleon. Discuss whether a kaon, a muon, and a pion each have the properties of predicted particle. Information about these 3 particles is on the data and formula booklet. Okay, so I would say the first thing to do is to look at what you need. Okay, what does this particle need to have, and make sure you go through the whole question looking for this. Don't try not, I know obviously there's a time constraint, but try not to rush too much. Think about it as you're reading it, right? The particle itself must experience the force. Okay, what particles experience that the force that holds the nucleus together? Well, it's the strong nuclear force, and therefore it would need to be some sort of hadron. Okay, there would need to be quarks involved. The particle would have rest energy between that of an electron and half that of a nucleon. So I'm looking at this thinking, well, this is 4 marks. This is some more of my marks, right? I'm going to check if they have a rest energy between an electron and half that of a nucleon. Okay. It's asking me to discuss a kaon, a muon, and a pion. So the 4 marks here is going to be, well, can it be the kaon? Can it be the muon? 1 mark is inevitably going to be for stating which one it can be, and the last one is going to be stating why, what it ticks about those, and what properties of that therefore does it have that sort of acknowledges all of this and is allowed by all of this. So essentially you're going to review each of these and you're going to state which one it is. Don't forget to do these steps and think about the marks. If you just make 2 points here, you're going to limit yourself to 2 marks. Okay, so first one, particle must experience the force, right? So I've got a kaon, that's a meson, that is a hadron. I've got a muon, and I've got a pion. Pion is a meson, which is a hadron. So muon is a lepton, okay, and I can see that on my sheet over here. So therefore And again, if you forget what the symbols are, right, you have your particle physics list here, okay, with the rest energies, and you have the symbols, and you can look down at your lepton number and see those symbols. Okay, so muon here is going to be a lepton. Okay, so I need to write something clear that muon does not experience the and show that you understand what you're talking about. Does not experience the, and I'm going to put strong nuclear force. And then why? Make sure you write full explanations for what you're thinking, okay? Don't just try and shorthand these, okay? Does not experience strong nuclear force as it is a lepton. Okay. Kaon and pion do both experience that. Okay. So we can add that in and say that the kaon and pion do both experience strong nuclear force, and that's what holds the nucleus together. But we need to eliminate these, right? So then we can put, well, kaon rest mass. So I would look again at my my data here, okay, and you can see there, if I'm looking at this, the kaon rest mass is going to be here you go, K meson. That's another, again, reminding you, right, mesons and baryons. It tells you where these are on this table. Okay, remembering these here are hadrons, mesons and baryons. Right, so the kaon is at 493, 497. Okay, and it's asking you to go between that of an electron and half of that of a nucleon. So nucleons are going to be obviously what's in the nucleus. So you've got protons and neutrons. Half of the protons and neutrons are going to be half of 438, 439. So you're looking in the region of about 470 there, maybe just shy of 470. So both of these are going to be above that. Okay, they're not going to be between the 0.5 of the electron and the half of the nucleon. So they are going to exceed that. Okay, rest mass exceeds half the rest mass of a nucleon. Okay, so that eliminates that, and therefore pion, you then need to say, well, what other, you need to, when you have this, even if you have the correct answer, just make sure you add in that you've checked it does actually fit everywhere, right? So the rest mass does exist between the two, so you can add that as a point. The pion rest mass exists between the two rest masses that you're going to allow. And then the last one is, does it experience the force? And you're going to state that pion does experience the force because it does experience strong nuclear force as it is a hadron. Okay, so the mark scheme for this, you can see here. The first one links hadrons to the strong nuclear force, or we're going to identify strong nuclear force as the force holding the nucleus together. So doing either of those. You can also have that by stating the pion and muon have correct rest energies with no mention of the kaon. So if you've done that, you do get that first mark, but make sure you're mentioning all three if you get listed 3 particles like that. Then you can see here, now we've mentioned the strong nuclear force, we're going to mention why it's not the kaon, we're going to mention why it's not the muon, those are our two, and then we're going to mention why it is the pion. Okay, don't just do kind of process of elimination and just say, well, therefore it's the pion. Say, why do you know it's the pion? Show that you've checked. Okay, why cannot be the kaon? The kaon rest energy is not between the electron and half that of a nucleon. You can quote the values from the data booklet. Reasons why it cannot be a muon. Muon is a lepton. See how it's underlined? You need to state this, okay? Therefore, it does not experience the strong nuclear force. Pion is the particle as it, okay, this is the key thing, right? As it has a mass in the range and it is a hadron, okay? Again, linking back to showing that you know what force they're talking about when they say the force that holds the nucleus together, okay? So it is a hadron and it has a mass in that range, okay? You can see here an incorrect statement about the particle negates the mark for that particle. So if you were to kind of waffle on a bit about these and try and get the mark as bulk, okay, don't try and do that, because incorrect answers will lose you marks that you have otherwise gained, okay? So you can see here, here's the rest energies that you can quote from the booklet as part of your working.